Great, thanks for that really nice introduction. Who knows what graphene is? Who knows how it was discovered? How? Somebody help me out. Sticky tape, it sounds good. So here is the mineral graphite as it comes out of the ground, and here is Scotch tape. So I'll pass it around and you can peel this, and if you peel down to a single layer, that's graphene. What else can you do with graphite? You can write with it, yeah. So a pencil is just graphite plus clay. So when this comes around, you're welcome to write with it. Yes, it was discovered in 2004. Novoselov and Geim shared the Nobel Prize in 2010. One of the things I love about UCLA is we have a lot of talented people here. And 4 years before Novoselov and Geim did their work, Tom Hahn from mechanical engineering knocked on my door and said, I understand you're a resident expert in carbon. Can you make me a single layer carbon? And I said, probably, but why would you want it? And he said, well, at the time, everybody's using carbon nanotubes to reinforce polymers. And he said, that's not going to work because you're going to have to orient them and they'll be too expensive. But if you had a layer, it would work. So he asked me how I do it. And I said, well, I would intercalate and exfoliate graphite. It's a layered compound. So we actually began our work much earlier than Novoselov and Geim. And we hold the world's first patent on graphene from 2002, 2 years before they discovered it. Okay, so today I'm going to tell you more about graphene. And here's graphene. It's a single layer of carbon. And you can think of it as the building blocks for all other forms of carbon. So if you want fullerenes, you can put in 12 5-membered rings and roll it up, make a sphere. You can roll it up and make carbon nanotubes, or you can stack it up and make graphite. Of course, these were all discovered much earlier, this in the Middle Ages, and these two in the last 20 years. So here's my favorite picture of graphite. In fact, here's the structure of graphite. And of course, graphene's just this top layer, which you'd peel off. But this is a block of pyrolytic graphite. This is what Novoselov and Geim used with Scotch tape. And this is about the size of your thumb. And what we're doing here is hitting it with a laser. This is from Neil Bartlett's lab where I worked about 30 years ago as a postdoctoral fellow. And this is being hit with a laser. And a normal material would heat up in 3 dimensions, but graphene, or graphite in this case, is not a normal material. So the heat follows 2 things. It follows what are called phonon modes, which are just chemical bonds, the bond stretches. And those all, of course, lie in this direction. These are not bonds, they're just van der Waals interactions. So heat goes this way, and it also follows conduction electrons, which are also in that direction. So you notice the laser hits here. If you touch over here, you burn yourself. If you touch the top, it's cold. And this is the only picture I've ever seen of a molecular property, or a nano property, if you will, in real space. Now, after Novoselov and Geim did their work, we started working on graphite oxide. Graphite oxide is, you can take graphite, and it's been known for 150 years that if you oxidize it with certain acids, that it forms a dispersion in water. So here it is in water. And when I say it's over 150 years old, here's a paper from 1860 on graphite oxide. And graphite oxide is nothing more than a sheet of graphene with carboxylic acid groups, hydroxyls, and epoxides. The question is, how do you get this back to graphene? And so we've looked at that, and we've made things like graphene paper, we've made electronic devices, sensors, oxide foam, lithography, and supercapacitors. And I'll focus on the latter, but let me just say one thing about graphene oxide. So the first thing we did is we made this graphene oxide, we hit it with a reducing agent, hydrazine, and it goes into water, and it is not a solution, it's a dispersion. The way you can tell that, it shows the Tyndall effect. If you put a laser in, for a solution, the laser go through, but you'll notice you can see the red laser, it scatters light. And so literally, it's single sheets, and they all have the same negative charge on their surface, so they stay apart. How do I know that? Well, if we neutralize the charge, we can put in salt like sodium chloride, it falls out. Because that neutralizes the charge on the surface, they fall out. And here are pieces by atomic force microscopy of chemically produced graphene. And you can see it's on the nanometer scale. So this is a paper we published in Nature Nanotechnology a few years ago. And a couple years after we published it, the editor-in-chief contacted me and said, congratulations, you have the most highly cited paper in the history of our journal. So most papers get 20 to 40 citations, and a really good one gets 100. This now has over 6,000 citations. Once you've made this graphene, you can stack it up. And here's graphene paper. We just ran it through filter paper, trapped all these layers. It's not graphite because graphite is actually three-dimensionally ordered. They go A, B, A, B. These are just random graphene sheets. But they're thick enough that you can actually fold them. You can see your reflection. This is a paper from Science a few years ago that we put together. But what I want to show you here is something called graphene foam. So what we did is we freeze-dried the stuff. It has this nice golden color. And I'm just going to light this on fire. What's interesting, it's not quite burning up. It looks like something's happening. And now we're going to take graphene oxide paper and hit it with a camera flash. Okay, so these are two very uncontrolled reactions. But imagine controlling this. And one way to do that is using LightScribe. And so this is something you may have gotten. It costs $25. You get it for your computer stack, and it's used to label CD disks. And so what we did is we told it to run this laser across, and we turned graphite oxide, which we put on the surface of the CD, into graphene. And you'll see we go from an insulator to a conductor. This is the current voltage curve. And here's what it looks like. So here's the plastic that we put this on. Graphene oxide is that golden brown color. We hit it with the laser, we turn it into graphene, and you can make any kind of circuits you like. In fact, we paid an artist for a picture of a human with a computer for a brain, and we reproduced it in laser scribe graphene. So the dark part is graphene, the light part's graphite oxide, and the other part is partially converted in between. Now what we're most interested in is using this for energy storage. Why energy storage? Well, when you need your computer and your cell phone, it's often not charged. The wind doesn't blow all the day. The sun doesn't shine all the time. So we're interested in storing energy. And here's a little graphic from Maxwell Technologies. They're the leading supercap company. Power is how fast you can deliver something. Energy is how much you can store. So a capacitor has high power. A battery can store a lot of energy. We're interested in supercapacitors, hopefully combining the best of both worlds. Now you can find supercapacitors. It's already a billion-dollar industry. They're used to back up power for cities. They're used to turn windmills. Batteries are too slow. You can recover over 40% of the energy from a crane when you drop cargo back on a ship if you have a supercapacitor. Again, you couldn't do this with a battery. And there's even a fleet of buses in China that run completely on carbon-based supercapacitors. So about every mile they put in a charging station. As people get on and off the bus, the materials get charged. And these things last millions of cycles. So these things work 24/7, 365 days a year. And here's my favorite example. This is in Amsterdam. This is a revolving door. It's connected to a supercapacitor that runs the lights in the restaurant next door. Human-powered energy. This is called the Ragone plot, power density versus energy density. We won't worry too much about it, but what we're looking for is electric vehicles. This is the Department of Energy's goal. So you want high power, you want high energy. And in theory, graphene can reach this. There's graphene on this same chart. However, this is based on the theoretical surface area of graphene, 2,600 meters squared per gram. And what happens is when you actually use it, in the real world, you only get about a quarter of that, of the farads per gram, the 550 farads per gram in theory. And the problem is these things restack. And if they restack, you lose surface area. But it turns out that our stuff doesn't restack. So all we did is we put a piece of plastic here, coated it with graphite oxide, told the laser to convert the whole thing. Cut a couple pieces and made a nice little cell. And this is going to look like a battery. It works a little bit differently. But here's the most important slide I'll show you. Here we told the laser just to draw stripes. So this is graphite oxide in one stripe, and there's the laser scribe graphene. And what's interesting is what we made. So the graphite oxide is this nice layered structure. After we hit it with the laser, it absorbs the light, it gets hot, it blows off carbon dioxide, and what we create is a fractal. And so these are sheets of graphene, but it's really disordered. It's three-dimensional, and it's non-collapsible. This is exactly what you want for storing energy because you have high conductivity, high surface area, and it's inexpensive. And this is a current voltage curve, and you'll see you get a nice rectangular wave. That means it's all capacitance. And this is versus a commercial cell. So the commercial cell, as it falls off, this thing keeps working. So we can store a good amount of energy with this. We can deliver it quickly. Now, if you look at the back of your computer, it doesn't work on our 1-volt aqueous cell or even our 2.7-volt non-aqueous cell, but it works at 14.4 volts and 4,400 milliamp hours. But you can get that simply by putting things in series and parallel. So here's 4 1-volt cells put in series, and you'll see we get out 4 volts. Here's 2 put in series and 2 put in parallel, so we double the voltage from 1 to 2 volts, and we double the area under the curve. And there's very little, these things are very low in internal resistance. And here we have the cycle life. Here we ran it for 10,000 cycles. It looks good. Here's the shelf life. We let it go for 4 months. And so these things look quite good. And if you put this on a Ragone plot, power density versus energy density, here's our aqueous cells or organic cells and ionic liquids. So they already start approaching the energy density of lead-acid batteries. And in the future, what we've been working on is we're putting battery materials into these, and now we can start approaching the energy density of lithium-ion batteries. But we think that graphene is a really good way to improve almost anything that involves electrochemical and energy storage. And if you want to read more, you can see this graphene for batteries, supercapacitors, and beyond. Now, I want to show you a short movie that was made for NOVA, the PBS program, just a couple months ago. We'll get it.
There's a lot of talk about renewable energy, but how feasible is it? A major barrier, believe it or not, is battery storage, and that's where something called supercapacitors come in. They run on static electricity, and they're capable of recharging and delivering power faster than batteries, but they don't store as much energy, yet. Enter chemist Rick Kaner. You see, supercapacitors are limited by the surface area available for holding electrons, and Kaner's developed a technique to produce electrodes with lots of surface area out of graphite.
This is what graphite looks like as it comes out of the ground. It's a mineral.
And this is what's in a pencil.
Absolutely. So a pencil is nothing more than graphite combined with clay. So this is the material that's used in essentially all batteries as at least one of the electrodes. So the question is whether you could make this in a high surface area form. And that is where graphene comes in.
Graphene is the strongest material ever tested. It's a layer of carbon that's 1 atom thick, giving it extremely high surface area. Kaner says 1 gram of the stuff would cover 4 football fields.
Graphene provides the high surface area and conductivity necessary to store large amounts of charge.
Which means graphene might just allow supercapacitors even more. And Kaner's lab came up with a surprising way to make it. It starts with plain old graphite. This is a chunk of graphite oxide that was mixed with water and then freeze-dried. Maher El-Kadi hits it with an ordinary camera flash.
Big flash. Yeah, it's just big. So just watch what's going to happen.
Okay. Oh!
The pulse of light's converted to heat, burning away the oxygen and leaving behind graphene.
That's graphene right there?
So what's left over, we call it now graphene foam.
Kaner's lab has developed a system to print exact designs. A layer of plastic gets coated onto the surface of a CD with a solution of graphite oxide. Once dry, it's inserted into a CD laser labeler.
That's wild.
But instead of doing its usual job of etching a label, wherever the laser hits the dried graphite oxide, that spot's transformed into graphene.
Oh! I like this technology.
Aside from a graphene likeness of David Pogue, El-Kadi's printed 2 graphene electrodes.
Obviously, there's a huge worldwide market for CDs with pictures of me in graphene, but I'm guessing that these are more important to the future of mankind. You etch circuits out of the graphene?
Yeah, so these circuits are basically micro supercapacitors. And this stores as much charge as these like very bulky capacitors that you will find in any electronic device.
You mean this totally flat pattern right now could hold as much charge as this capacitor?
Yes, and we actually made them store 1,000 times more charge as this size of a capacitor.
If we could scale this to the size of electric vehicles, then you could actually, instead of pulling into a gas station, you'd pull into a charging station, and within minutes, your car would be ready to go.
An electric car that you can charge as quickly as it would take to fill up?
I would definitely like to see that happen, and that's exactly what we're working on. Wow. Okay, with that, let me thank my students who have done all this work. And also, I need to acknowledge Nanotechnology. It's a company we started recently to try to commercially develop this technology. So thanks for your attention. I'm happy to answer questions if there's time.